All right, class. Welcome back. Now we begin to move forward from where we left. And I want us to do something very important. Therefore, I'd like to ask you to pay attention. We need to go back to the foundation because in engineering drawing, if the foundation is weak, as I said last time again, everything that comes up thereafter becomes pretty difficult. And from your feedback, and I really appreciate those who've reached out, it is clear that we need to slow down and build this properly. So today is not about rushing ahead. Today is about clarity. And let's begin from or with something very simple. A straight line. The shortest distance between any two points is what we call a straight line. Now that sounds obvious, definitely, but in engineering drawing, the idea is extremely powerful. Think about an object around you, a machine, a component, whatever you can just say around a structure, mechanical part, etc., or you're drawing instruments. Yes, all of them are made up of surfaces, and those surfaces are bounded by edges. What are those edges? They are lines, or let me say straight lines, okay? Now, so in reality, points define position, lines define edges, and planes define surfaces, solids define complete objects. That means the straight line is one of the most important building blocks in engineering drawing. This is why projection of straight lines is not just another topic. And thank you for those who raised up the issue of wanting me to do a repeat on the same orientation or just orientation of lines and their projection. Okay. Now, if you understand lines properly, planes become easier, solids become easier, visualization becomes natural. So today we are strengthening this foundation. From our previous lesson, we already know how to project a point. Now, think about this. If I take 2 points and I join them together, I form a straight line. Call this point A, point B. I join using a line or it's just a straight edge, it becomes a line. So what happens in projection? Very simple. Very simple. If you join the projection of 2 points, you get the projection of the line joining those 2 points. Now, today I'm going to use my board actually to do one and the same. Okay, before even we get to proceed later at the end of my introduction. Okay, now, so today is a recap. Our objective is very clear. First, we understand the space in which objects exist. The space in which the object exists. Then, two, we understand how points behave. Third, we build how lines behave in different positions. And this time, we will not memorize. We need an understanding. And that's why I'm laying this foundation once again. Now, before we go deep into lines, we must first understand something very profound and very important to us. How a space or space is defined in engineering drawing. And in engineering drawing, we describe the position of objects using reference planes. The two planes are the vertical plane and the horizontal plane. Let me use that for our understanding what a projection. Now, I mentioned about the two planes, the vertical plane and the horizontal plane. Well, I have illustrated using the slide on your screen. These two planes intersect each other at right angles. And the line where they meet is called the reference line, XY. Okay? Now, I would want to go straight away into just quickly demonstrating what I mean by this. Okay? And allow me just today I'll be drawing with you, together with you. I'm taking my ruler here and I really want to project a line so that I may explain what I'm talking about. Now, ignore what is on the screen and straight away I'll just use I'll draw and I need to pick up my ruler now. I want to draw an horizontal line. Okay, here it is. I'll draw an horizontal line and I want to draw a vertical line for you. Now, as you can see here, okay, let me just zoom and mark for you. You see that I have drawn two lines. Now I can vertical and horizontal line, and I said again I gonna label because it's very important for us to do what, to understand what I'm doing here. Now let me call this one an X, okay, and this one a Y. This is the XY line. Now I'm assuming we have what, 2 points, okay, this point A and this point B, or point X and Y in a straight line. They form what we call a reference line. Let's shift back to our discussion. Now, when these two planes divide the space, they create four regions. The four regions already we've just seen them here in our drawing. Okay, that's the first one, the second one, the third one, and the fourth one. Now I'll label them. Okay, apology for that. Let me label the four regions for understanding. Okay, instead I will just basically take the four regions. Okay, one, there's the second one, third one, and the fourth one. Beautiful. Now, what are these four planes that we're talking about? Basically, the four planes are what we call quadrants. Let us define them clearly. The first quadrant, the first quadrant that you can see as one is above the HP, in front of the VP. I explain again and I repeat again. It's above the HP, but in front of the VP. What do I mean by that? If this is the reference line XY, as you can see, I'm hovering over for you to see this one. Okay, now it's above the HP. What do we call the HP? This is the HP now, the horizontal plane. You can only see the horizontal plane if you're viewing it where? From the top. So in that case, if I'm just again to basically uh, position that, I will just say you can see that one from the top. I just but one an arrow here. Okay. Okay. Let me just do a neat one so that at least you're able to view it. Okay. Now that's way much better. Now you'll be able to see what you call the HP. Okay. Let me just draw a neat one. Okay. Here too. In this, the horizontal line, that is the YZ, oh no, the Z, is what gives us what you call the HP. Now, when I'm saying, and I'll pick again, let me undo this one. When I'm saying that it's above the HP, but in front of the VP, there is what we call the keyword observation. Where are you observing from? That's the key word that I want to get your attention. Now, in the second quadrant, it's above the HP, but behind the VP. We've defined the VP, we've defined the HP. So the second quadrant, where is it? To the second quadrant. It's above the HP still, but behind. Now on the third quadrant, we just see that it's below the HP horizontal plane, the XY reference line, but behind the VP again, but behind the VP. Note the following. Note the following. It's very important and very crucial for you to understand that when I'm saying behind, still the vertical line is crossing the XY plane up to the third one. Still it's behind. But here, from this side, even so forth, is in front. Is in front, is behind. We're talking about the VP. Above, below. Above, below. Pay attention to two things: above, below, behind, and behind. Single period. The reference line is right in the vertical line that gives you the division at the point of intersection, the four quadrants. Now, finally, the fourth one is that it's below, as you can see here, it's below what? The VP. No, it's below the HP, but behind, or no, but in front of the VP. So we've made this very clear. So every point or line is located based on what? Based on its position relative to the HP. Now, class, this part is very important. When do we do projection? Because that's what we're here today, projection of lines. And that's what some of you raised a question for me to repeat again and more so go deeper into projection of lines. The object does not move. Pay attention. When do we do projection? The object does not move. The quadrant does not change. What we do is we project the object onto the planes. One, then rotate in the horizontal plane clockwise by 90 degrees. Remember, I'm talking about rotating the horizontal plane. Okay? Now start to visualize, don't memorize, okay? And above the top views lies on the HP. It comes with the plane into the final position. So before we go back to the lines, let us remind ourselves. A point has no length. It's very important here now. Okay? Its length is negligible or just has no length. Period. It has no width. Therefore, its width is negligible. But it has only position which can be defined by coordinate systems or just whichever way you want to define it. Okay? Now, when we project a point, pay attention to this. Its front view appears on the VP vertical plane. Its top view appears on the HP. I repeat again. Two very basic things. The front view and the top view. Allow me to just maybe go back to the main slide here for you to understand what I'm talking about. Very important. Okay. Now, we have what you call the coordinate system there, the VP and the HP. You can see where I've just written the top view and the VP in the slide. And that's what I'm just referring to. That its front view appears on the VP, its top view appears on the HP. Now, the final positions depends on whether the point is above or below. I repeat again. The final position depends on whether the point is above or below what? The horizontal plane HP. And two, in front or behind VP. Am I clear on that one? I think I'm making things more simpler. Now, we are ready to return lines. And this is where everything connects. Because a line is nothing more than 2 points just joined together. Simple period. Just 2 points A, B joined together and you have a line. So if you understand how to locate a point and how to project a point, then projection a line becomes logical. But now comes the most important question. Sometimes it appears as a full line. Sometimes it appears as a short line. Sometimes it even appears as a point. The answer is very simple. It depends on the orientation of the line with respect to HP or VP. I repeat again. I've just said when projecting a line, it can be seen as a point, it can be seen shorter, it can be seen as the actual length of what is being projected. Now, what depends, what causes all that orientation of that line with respect to what? The HP and VP. In VP, we said about two things: behind, behind, and behind. Are there more than two? But summarized into one. But what about the HP? The same manner: above, above, or below. VP, behind, in front or in front. On top, VP, HP, below HP. So that's what will give you either point, an actual length, or an inclined length, or not an actual length of a line when it's projected. So now we understand the coordinate system. The reference plane, I've just used the XY and the dream cursor for your understanding. And we've understood about the 4 quadrants as projected here. Now, we also know when we are observing, it matters the point or the line of sight. And our points form lines. We are now ready to answer the most important question. How does the position of a line affect its projection? To answer that, we now introduce the different orientation of lines. Okay? Different orientation of lines. One, or even before I get to talk about this orientation because it's important as we proceed. This is where the real understanding of projection of lines begins. To this point, we have understood how space is defined, how points are projected, and how a line is formed from 2 points. Now the next question is, why does a line appear differently in different views? A line. And the answer is found in what we call the orientation of what I've just said above. Now, these are the 6 orientations above. A line parallel to the VP and perpendicular to the HP. A line perpendicular to VP and parallel to HP. Or when a line is parallel to both the VP and the HP. What about? Is it always on perpendicular or parallel? No. It can be inclined to the VP, that's the 5th orientation, and also parallel to the HP. Or and also I skip the 4th one when it's parallel to the VP, but inclined to the HP. And finally, when it's inclined to both the VP, HP. Note, parallel and perpendicular, and vice versa to VP and HP. Parallel to both, inclined to VP and HP, and vice versa. Inclined to both VP and HP. 6 orientations. What do I mean by these orientations? Orientation simply means a line is positioned in space with respect to the vertical plane and also the horizontal plane, of which we've just defined using the XY reference line. And so we say it above, below, in front, and behind. And that relationship determines how it appears in front, in the front view and the top view. Now, I will introduce and we'll just start to walk from case to case. But before then, there's something I need you to understand here about these orientations. Yeah, that's what you call the positioning of lines. Okay. Now, before we start to draw each orientation one by one, I've talked about the 6 orientations. We need to understand something very important and pay attention to what I've just projected on the screen. The slide is just a summary logical projection of lines. If you understand this table, every orientation we draw next will make complete sense. Let us first understand this table, what this table is showing us. Basically, the table is connected 4 key ideas. 1, the position of the line in space. Secondly, what we see is the front view. Its position of that line in space when is being projected to see what we call the top view, and whether the lines has what we call traces, a trace. So this is not just a table, it's a complete relationship between space and projection. If we go back again to our discussion, we talked about very simple about line and space, above and below. And allow me to say this. Everything we discuss here is always relative to XY line, relative to VP, and relative to HP. Very important. Very important. And this is the most important idea of this slide. If you skip or you're missing something or you'd like to raise a question, just write it down in the comment section. Please ensure that you've just raised up an query. I'll be able to answer. I'll check all the raised questions and I'll be able to respond to them. And if there's anything that you think that I should again repeat or just explain further, do as well in the comment section. Thank you. Now let's proceed. This is the most important idea in this slide. A line shows its true length in the view when it's parallel to the plane. Oh, this is very important. And it brings me back to our first semester, when especially we were just drawing inclined lines in the, not only drawing inclined lines, but dimensioning an inclined line. Most students tend, and let me just let me say this, do this. I need to really demonstrate this using my notebook here, which is very important for us to understand. When the students I tend to draw parallel lines, for example, this one here, dimension and length. Here we have I want to use for example this one. Let me refer to this diagram here. Okay, this diagram here. Now, I have inclined this line at 30 degrees. Okay, that's what you call an isometric projection as an isometric line. But now, if I tend to draw a line, a dimension line this way, pay attention, please. Okay. Now, this, as you can see, is exactly 30 degrees inclined. And if I draw a line that is parallel to that one, it gives me what you call the a true length, a dimension if I dimension it. But now, this is where students don't get it right. From the word go, a student comes and just says this, okay? Check this out. Instead of doing a parallel dimension, now it just takes what we call a word ruler, just draws without inclining it, and voila. And now it tells me that well, if this side, okay, was exactly 60 say millimeters. Now it tells me that this length is what is parallel to what to this one. Is that a position? Is this length equal to the actual side of this plane? No, 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 no. Since I go back again to what just said there before in my explanation, that a line shows its true length in the view where it is parallel to the plane or to that plane. Parallel to a plane gives us what we call the true length in that view. Let's start with the simplest case. If a line is parallel to the both VP and HP, it would incline to end plane. So the front view shows the true length. The top view also shows the true length. And both are parallel to X and Y. Also, there are no traces. Why? Now refer to the table 3. I would want you to refer to the table projected here for you because I'm explaining better on that one. Now I said there are no traces. Why? There are no traces. And what is a trace? We have either vertical trace or an horizontal trace. I'll explain that. Because the line never meets any plane at all. Let's come to the second case scenario as per the table. A line perpendicular to VP in parallel to the HP. Now, it's very important. The line is perpendicular to the VP in parallel to the HP. So, since it's perpendicular to the VP, perpendicular means meeting at right angles, 90 degrees, in front view, or its front view collapses into just a point. I'll demonstrate that. Or maybe I need to do, yes. I'll have to use one to just demonstrate that later. Now, since it's parallel to the HP, its top view shows the true length. Let me do it. It's good for us to understand what I'm just saying right away. Now, let me just proceed to something else. Okay. Now, we are using the first quadrant and the second quadrant. Let me use it just to draw a line here above, and I want to make that sure that it's what at 90 degrees, and I'm gonna change what we call maybe probably the pen and the ink color, and it remains the same, but in this case I'm gonna draw or just a line. Now I want to strike this point along the second the first quadrant. I have just about finished, and now let's just view it perfectly. Here it is for you. Now pay attention to this section. This line is parallel to the HP. It's parallel to the HP. What if the line of observation? Let me just again go back to the drawing. If the point of observation, okay, the point of observation is from where? It's from here, okay. This line, what will you see if you are the observer? Okay, let me just say this is the observer from this position. That's the point of the observer or the observation point. What will you see straight away from this point position? What you just see, this line is just but something like a point, a dot. But if you are from here, the top view, okay, you're viewing from the plan as shown by this arrow. Okay. Mhm. This line will be reflected where at the HP equal to its actual length. And here you are able to see its true length. But from this point, you can't tell the length from the point of the observer. But until you change the position from the top, is when you'll be able to see that this line is approximately this kind of, let me say, 50 units or say 20 units. Okay. But from the observer perspective, it's just a dot because it's just a but it should just be seen at the VP as as just a dot. But on the HP, it will be seen you see its true length. Beautiful. Now, since it's perpendicular to the VP, front view collapses associated again. And since it's parallel to the HP, top view shows the true length, and that top view is what you call is what we say is perpendicular to the x y axis, or just reference plane. Next, pay attention, please. It's important. Now, in this case, in the second case, one vertical trace exists, no horizontal trace. Now let's go to the third scenario. The third case, when a line parallel to the VP perpendicular to the HP. We are discussing about the positions of lines before we go to each individual slide, each individual water specific orientation, and I'll be able to give practical examples. Now, this is the reverse of the previous case. The line is parallel to the VP. When I'm talking about a line being parallel to the VP, you understand what I mean. Just straight away, I can just project a line parallel to the VP. It's simple. This is the vertical plane, and I'm gonna use a different color now. In this case, I will just draw it behind, or let me just draw it in front. Okay, because we're gonna come to this is 90 degrees, perfect. Okay, let me now use in this case I use a dark green color, and I'm gonna do what I'm gonna draw a line which is parallel to the, and I want to draw two of them, both in the the first and the fourth quadrant, for our future reference. Okay, here they are. These are the lines. Okay, and this is another line. Okay, now pay attention to what I'm just saying or just demonstrating here. Mhm. We said that in this orientation, or in this case, line is parallel to the VP but perpendicular to the HP. So the front view shows the true length. It's perpendicular to the XY reference line. The top view is just seen as a point. There's no vertical trace in this case scenario, but only the horizontal trace. Okay. The fourth case, when a line is parallel to the HP and inclined to VP. Now we introduce what we call an inclination. An inclination is what I just demonstrated, where students and in our first semester used to have this kind of difficulties of drawing what we call a dimension line to an inclined line, and that dimension line is not parallel to the edge or the line, the line of the object that is being dimensioned, and we call that line, yes, it's inclined, but it's not parallel. Therefore, it's inclined to this the surface. Okay, now the line in this case, the line is parallel to the HP, one, and inclined to the VP. So the top view shows what you call the true length and true inclination. The front view is always shorter than the true length. I'll demonstrate that when we come to the actual orientation part. Each and every orientation, I'll go deeper. Now, this is what we call apparent length. When the front view or the front view, okay, the true length is shorter, is what we call the apparent length, and it remains what parallel to the xy. So in this case, only the vertical trace is available, no horizontal trace. In the fifth scenario, the fifth case is when we have a line inclined to HP in parallel to the VP, inclined to the HP in parallel to the VP. Well, the line is inclined to the HP in parallel to the VP. So what do we have here in this case? The front view. Remember, we're talking about only two views: the top view and the top view and the front view. So the front view shows the true length and the true inclination, whereas the top view is shorter than the true length. And this is what I defined there before as the apparent length. And when it's parallel to the x, you realize that you cannot have a vertical trace but only a horizontal trace. And finally, in the last, the projected slide, the position of a line when it's inclined to both the VP and HP. Now, the most generous case, why I call it generous, is simply because the line is inclined to both. So neither the front view nor the top view shows the true length. So both views are shorter than the true length and are inclined to the x and y line or reference line. Also, the angles you see are not true inclinations. Okay, so this is the only time because generous kind of inclination, it has both traces, the HT and the VT, as in the horizontal trace and the vertical trace. They do exist. So let's summarize the entire table in one simple rule. A line shows its true length in the view when it's parallel to the plane. Two, if it's perpendicular to the plane, that view becomes a point. I want that one to sink. If it's perpendicular to a plane, that view becomes a point. Three, if it's inclined, the view becomes shorter than the true length. Good. One, a line shows its true length if the view where it's parallel to that plane. Secondly, it is if it's perpendicular to the plane, and that view becomes a point. And if it's inclined, then the view becomes shorter than the true length. Many students try to memorize this table. Please don't try to memorize. But it's not because it's not necessary. I want you just to understand what we call being parallel, a perpendicular thing, and also an inclination terminology that has been applied here in most cases. You can predict every result once you know when it's parallel, a line, when it's perpendicular, and when it's inclined. So let me ask you, if a line is parallel to the VP, which view will show the true length? Type on the comment section. I repeat again the question. Type on the comment section with your identity. I just want to see this, and do not copy from another. Now, open. I repeat again the question. If a line is parallel to the VP, which view will show the true length? Okay, I'll check it out, but that's food for thought. But the answer is the front view. Now we understand the logic. We are ready to apply it. Now let us take the first case in the list and construct it step by step. The first case is what we call the first orientation as the line parallel to the VP perpendicular to the HP. Beautiful. Thank you. Now, let's move forward. In this first orientation, we are discussing when a line is parallel to the VP and perpendicular to the HP. I have projected a slide whereby I have used the presentation as both what we call the orthographic pattern in the isometric pattern as well. Okay, isometric shows the 3D, whereby we have the vertical in the horizontal views, but whereas the orthographic just only shows the top and the front view in that position. Now, class, let us begin with the first orientation, a line that is parallel to the VP. A line that is parallel to the VP and perpendicular to the HP. This is one of the most important cases because it clearly shows how a line behaves when it is standing upright. Upright. Okay. Now, what does it mean geometrically? As you can just perceive in the orthographic pattern. Parallel to the VP, the line is facing the vertical plane. Parallel to the HP, the line is standing vertically. So you can imagine this line like a vertical rod standing on the ground. Let me just say a rod or just a flagpole. That's a good example. Okay. Let us start with the pictorial presentation here that you can see. The vertical plane, it has the vertical plane, it has the horizontal plane, and line AB is standing upright. Now observe carefully. The line is perpendicular to the HP. That means it's vertical. And since it's parallel to the VP, we see its true shape clearly. The true shape, it can give us also the true length in the front view. Now let's apply the main rule from the table as we just learned. Line shows its true length in the view where it's parallel to the plane. Did we learn that? From our previous table that was summarizing the position of a line in various orientations? Yes. So, when the line is parallel to the VP, the front view shows the true length. You can see it in the orthographic pattern above the HP. But since the line is perpendicular to the HP, the top view becomes a point. Now, let's move to the orthographic pattern. Now, let us. Okay, I needed to just use another. Let me check on one note quickly if it can really give me this view. Okay, it's up and running, but I want to believe that it has to respond quickly. Okay. Yes, thank you. I've refreshed. It's responding perfectly. I just want to demonstrate here because maybe the 3D observation there may not give us what we really want. When I'm taking I'm taking this first case from the list. One moment. Yes. Now, as we can see, I have drawn what you call the reference line. All right. Now, since the line is parallel to the VP, I drew using a dark green color just a line in front of the VP. And this represents the true length of the line. The true length of the line can only be seen by from the observation point. Remember, always we've written as one perfect spot of the observer. And this represents the true length of the line. So if you are just to solve for this, in this case, how do you continue with this orientation? So there are three steps. The first step in such a case is just to draw a reference line. Okay, after I have drawn in that one, the line XY. The second step is just to draw the front view. Okay, now since the line is prior to the VP, I have drawn the front view. A prime, B prime, the vertical line. Pay attention. Remember when we just were talking about orientation earlier on, I said A, B, and A prime, B prime, and also A double prime and B double prime to represent various views as the plan, the front view, and finally the side view. And this representation the true length of the line. I mean A prime, B prime as a vertical line. Okay, step 3, before to draw the projectors. From the endpoint, I have projected downwards. Pay attention to the HP. I project downwards to the HP. And then the next step, what I've just done, is now for you to observe what you've just done. Now, that's what we call visualization. You observe. Since the line is perpendicular to the HP, both endpoints project to the same point. So the top view in this case scenario becomes a point labeled as A, B, not A prime, but A, B. Why does this happen? Oh, sorry, why does this happen? Because when you look at a vertical line from above, you only see it as a dot, a point, a vertical line from above. Okay. So the entire length collapses into a single dot or just a single point. Remember, projection of points in lines. And I define what a point is, and the connection of 2 points becomes a line, etc., etc. Now, let's interpret the dimensions. You can see the front view shows the true length, the front view. Pay attention closely. You can zoom and check that one out. Now, say it's approximately 25 units. The front view of this point is located relative to the XY reference line axis. And above the XY is the distance from the HP. Below XY, projection onto HP. I repeat again, the position of the HP is located relative to the XY. When it's above XY, we just see the distance from the HP, but when it's below the XY line, we see the projection of onto what we call the HP. And the top view is shown as a single point below XY, the dot. So let us just summarize this slide or just this presentation as such. 1. If a line is parallel to the VP, the front view shows the true length. 2. If a line is perpendicular to the HP, the top view becomes a point. Please pay attention to this. These are some of the common student errors, and I really need to address them here. Many students make this mistake. They try to draw a line in the top view, but that is incorrect. In that case, the top view must be a single point, not a line. Let me ask you, if I take a vertical pole, use a flag in this case, and look at it from above, do I see its full length or just a point? Can you have your answer? Just draw with me a vertical line, or just hold your pen vertically, place it on your desk. And now, because your pen is shorter than that, try to stand and just look at it from above. Okay, what will you just see? More of a point. But in front of you, put it in front of you. Okay, what will you see? Its true length. This is exactly what is happening here. So, what are your key takeaways? Parallel to a plane gives the true length. Parallel to a plane gives the true length. Perpendicular to a plane gives you a point. Are we good? Now let us move to the second case where the line is perpendicular to the VP in parallel to the HP. And here we'll notice everything we have just learned will reverse. I mean the opposite of that. So I want to give you a quick thing to do. Quickly, note down, practice. You draw a line XY. I want to give you how to solve such a case. Okay? Just sketch it quickly. And draw a vertical line the way I just done. Okay? Draw the projectors. Mark single points below the top view. Label A prime, B prime, in A and B. This is what I want you to emphasize or to note down. Perpendicular collapses to a point. Parallel shows the true length. Don't memorize this, please. Visualize it, please. Okay, let's move to the second orientation. A line perpendicular to the VP and parallel to the HP. And we'll continue building step by step. Here we go. Well. Line perpendicular to the VP and parallel to the HP. Let us move to the second orientation. I want you to observe something very important here. This case is the reverse of the previous one, which makes it easier even and more enjoyable. Okay? What does this mean geometrically? When I want us to interpret the position perpendicular to VP, perpendicular to VP. Okay? It means that the line is pointing directly in front or oh no, it's directly or away from the vertical plane. Away from the vertical plane. The vertical plane is the HP. So away, it means that line will only be parallel to the HP. But from the point of the observation, as you can see in the point, it gives you what we call a dot on the VP. It's reflected as just a dot. It's like you're using a spotlighter during the dark times and just holding an object and being and checking the point of a point of projections, right? The object is reflected on the back end of the wall. Now, prior to the HP, the line is lying flat on the horizontal plane. So imagine this like a rod lying flat on the ground, but but pointing straight towards a wall. That's another good example I can just give you to visualize. Now, here on this left figure is a pictorial view. Note, when I'm talking about the pictorial view, more of what you understand is more of isometrically drawn, and orthographic is in 2D. Okay, here's a pictorial view. You can see the line AB lying on the HP. The left, there are three diagrams here. The left one I'm talking about. It's not inclined, it's flat, but it's directed towards the VP. So when we project this, we apply the core rule. And what is the rule? We learned previously from the table summary. A line shows its true length in the view when it's parallel to the plane. Okay? A line shows its true length in the view where it's parallel to the plane. So, since the line is parallel to the plane, and this plane is HP, horizontal plane, the top view shows the true length. The top view shows the true length. But from the point of the observer, it's reflected towards the vertical plane, and it's just seen like a point. When it's perpendicular to the VP, the front view becomes a point. Now, the middle figure here, the orthographic pattern. Now, let us construct this step by step. Please sketch with me. Take a paper and a pencil, sketch and think, sketch. So, You've known how to draw an X, Y. The reference line is horizontal. Do that quickly and label it with whichever units you want to give it approximately. Okay. The next step, draw the top view. You start from the HP. Since the line is part of the HP, you'll begin with the top view, AB. Not A prime, B prime. A, B is a line, just 2 points. The starting point and the end point. This shows the true length of the line. Okay? When you draw horizontal or vertical segment, depending on the orientation, clearly below HP. Okay? Now the next step, the third step is now you project it upwards. You project it where? Upwards. From all points A and B, project upwards towards the VP. The next step, now visualize by observing. Since the line is perpendicular to the VP, what do you see? Both points project the same point. I mean, yes, there were 2 points A, B, but now when you're looking from one end, both points coincide with each other. That's why I'm saying both points project to the same point. So the front view here in this case becomes a single point labeled B prime, A prime. You've just completed that. Why does this happen? It's simply because when you look at a line that is pointing directly towards you, you only see its end. So the entire line collapses into a single point in the front view. Beautiful. Now, why do we have the third right figure on your right? The train. Pay attention and work with me, please. Catch me if you can. Now, looking at the dimensions, the top view shows the true length. Let me say approximately 25 units. I will be referring this. Okay? The point is positioned relative to the XY. Below the XY, on the HP horizontal plane, above the XY is the front view position. And the front view appears a single point above the XY. Wait, wait. Now, let us summarize this case. Part of the HP, top view shows the true length. Perpendicular to the VP, front view becomes a point. I want to highlight common student errors in this case most of the time. Students often try to draw a line in the front view here, but that is incorrect. The front view must be a single point. It cannot give you the actual length. So let me ask you, if I take a straight rod and again I point it directly at you, will you see its full length or just a point? Now, you have your pen and paper for schedule purposes. Draw an horizontal line as the top view. Dot above XY as the front view. Say, I repeat again, draw an horizontal line as the top view and a dot above the XY as the front, horizontal line as the top view and also the dot above the XY reference line as the front view. This is exactly what is happening here. Now, we've done the first case. We're in the second orientation. Let's do what we call a comparison between the two of these cases: the previous case, the first case or orientation, and the second case orientation. The first orientation, where did we get the true? Before we do this, I need just to jog your mind. I just want to see whether you got it right, and draw for me in the comment section. The first orientation, where do we get the true length? Where do we get the true length in the first orientation? Quickly. And in the second orientation, of course, I've just explained. We know the orientation now. Please drop in the comment section quickly. In the first orientation, where do we get to see the true length? In which view? Is it the top view or the front view? Or vice versa, whichever. Now, I can see comments coming here. Okay, comments, please. I'm just waiting to see, because I need to understand that you guys are with me here and you're getting what I'm asking. Beautiful, beautiful, beautiful. Now, let's proceed. In summary, I can just say, in the second orientation, we can only see the true length in the top view, in the top view, and just a point in the front view. And vice versa, because it was the opposite of the that one, the first orientation. The front view gives us the true length, and the top view gives us a point. These are exact opposites. So, what should you take away, please? A parallel line gives you the true length. A perpendicular gives you what you call a point. Which view shows it? Depending on the plane. Parallel to the line gives you the true length. Perpendicular to that line or gives you a point. And which view shows it? It depends on the plane, whether it's on the HP or the VP. Now let's move to the next case. In this case, it's the third case, where the line is parallel to both the VP and HP. And this one would be very interesting, and even more interesting, because both views would be now showing true length parallel to both the HP and VP. So this exercise, I would like you to do the following. For the second orientation, you draw a line XY. You draw the top view as the true length. And then you project upward and you draw a single point, which is the front view. And you label A, comma B, and A prime, B prime. Here we view parallel to the plane is what gives us the true length. The view perpendicular to the plane is what gives us the point. And this is just not a new rule. It's the same rule applied differently. Now, let's move to the next slide. Thank you. Align parallel to both VP and HP. Here we go. Now, a line that is parallel to both these planes, the VP and the HP, is our third orientation. And in this case, it's very important because it's the simplest orientation for all. I'll be using this as standard method of presentation, the pictorial drawing, the photographic pattern, and also the actual practice on how to solve it, which will give you just a basics to understand how to always solve such cases. Okay, what does this mean geometrically? Starting from the beginning, the line is parallel to the VP. Factual. 2, the line is also parallel to VP or to HP. Beautiful. Facts. The line is not tilted, it's not inclined, it's not vertical, just parallel to both. It's simply lying straight in space without any inclination, which is as demonstrated in the pictorial drawing on your left diagram that you can see. In this pictorial view, you can see that line AB, which I've just got projected there, just got marked there, is parallel to both planes. It's neither standing upright nor pointing towards the VP. Pay attention, please, important. So it's in the most natural position. Now let's apply our main rule. What was the rule that we obtained from the previous table? As a summary, a line shows its true length in the view where it's parallel to the plane. But here, the line is parallel to both planes. So what does that mean? The front view shows the true length. The top view also shows the true length. In this case, both views show the true length. If we've summarized, we don't have to go further. Simply because we have the orthographic pattern, I need to explain why I just had to give this. Now, in the middle diagram of the figure of the orthographic pattern, let us now construct this step by step. As I said again, you're going to work with me. Yes, with your paper, you'll be sketching, I'll be guiding you. What you need to do here is just as usual. Remember always our starting point, the reference line XY. First step, you've done it. Okay, the second step, draw the top view. Since the line is parallel to the HP, draw the top view as AB. Give it a length. You start with what is known to you, that's the true length, and we say AB is approximately 25 units. In this case, I'll be using 25 units now, and this is the true length of the line. So the third step, you just project it upward. From points A and B, project it upward to VP, as in the vertical plane. In the fourth step, just to draw the front view. See, the line is also parallel to the VP. The front view, A prime, B prime, is also drawn as a line of the true length. I repeat again. Since the line is also parallel to the VP, the front A prime, B prime, as indicated there, is also drawn as a line of true length. Now, this is a very important detail. Observe something very important here. Both views are parallel to the XY line. Why? Because the line is not inclined to either plane. Let's move to the right figure, the third one on your right on the screen. Now from the dimensions, the true length, say, we just study units, okay? Both the front and the both front view and the top view shows the same length. The only difference is their position relative to XY. When I'm talking about the position is, remember when I was just talking about behind, in front, above, below. So in this case, I'm talking about the position of relative to XY. In this case, the front view is above the XY, HP. The top view is below the HP, XY, the reference plane. So let us summarize this case very simple. Parallel to the VP, the front view shows at the true length. Parallel to the HP, the top view shows at the true length. Parallel to both views shows us the true length. Voila, you're done with this. So please don't make these common mistakes again. Thinking one view must always be shorter. It's not always. I'm talking about the common student mistakes. But this case proves that it's not always true. Both views can show the true length. But previously, the first and second cases we've seen differently. Okay? Now let me ask you. The question, please. If a line is not inclined to end plane, should any view be shorter? If a line is not inclined to end plane, is it longer or shorter? Just for your learning. Quickly, Just draw a line, reference line quickly, sketch it, draw the line below xy. Oh, a sort of line, of course, above the xy, okay? The same line below xy, or about a point symmetrical, okay? They both the same line in different planes. Now let us compare these cases. We've done the first case, the second case, and now we are in the third case. Okay? In the first case, orientation, the true length was on the front view. The second one, the top view. The third orientation, when a line is inclined, is parallel to both HP and VP, we've seen that the true length is shown on both views. So this is the most balanced case, a fair one. When a line is parallel to both planes, you take away. No distortion occurs in either view. Now, things start becoming more interesting. We are now going to introduce an inclination. Initially, we said parallel to VP, parallel to HP, perpendicular, and vice versa. We've done what we call parallel to both. We've not talked about any inclination. So the next fourth orientation will be a line parallel to the VP, not perpendicular, parallel, but inclined to the HP. And here, one view will remain true, and the other will change. Now, your summary and for this assignment. Okay, draw a line XY, sketch it quickly. Draw the top view, which gives you the true length. Project it upward. That's the next step. Draw a front view, same length. Show both parallel to the XY reference lines. Sorry. So the key concept here is that they are parallel to both planes, and both views shows the true length. This is the only case where both views remain completely undistorted, and that gives us an option to move to the next fourth orientation. Hanging on there, we're about to finish. Line parallel to the VP but inclined to the HP. Now, in this case, this is where things start to become more interesting. Why am I saying this? Because up to now, the lines were either parallel or perpendicular. Now, we introduce an inclination. In this case, the line is parallel to the vertical plane and inclined to the horizontal plane. So what does that mean? The line is still facing VP directly. But it's tilted with respect to HP. When I'm saying this, please pay attention to the slide. We have a pictorial as a presentation. I've used the same standard method of graphic pattern and the actual solving of such a problem. If you had faced such a problem and you need to know to draw it. Okay. Now I want you to refer to the pictorial image in the left or on the left of your screen. Let us understand this visually. Okay. You can see the line AB, right? It's not flat on HP anymore. It's lifted at an angle theta from the horizontal plane. Give it whichever angle you want to adjust. Okay? But observe carefully, and I repeat again, observe carefully. It is still parallel to the VP. Parallel to the VP. Yes. Now let us apply our main rule. Remember the rules? What just was summarized in that on the table that we talked about. Okay, about the orientation. A line shows its true length in the view where it is parallel to the plane. So here is parallel to the plane. The front view shows the true length. Even to the HP, the top view will not show the true length. Oh my. Kind of interesting, right? The front view in this case shows the true length plus the inclination angle. The top view is shorter than the true length. And initially, I introduced what we call the apparent length, a shorter length that is not the true length, is known as apparent length. Now let's move to the orthographic projection in the middle. What do we see? Let's construct this step by step. I want you to work with me because I want you to understand. And at normal, be sketching with me. Now, sketch what we call a line XY line, reference line, quickly. Label it as XY. First draw the X reference line, okay? Now, the next one is you start from the front view. Since the line is part of the VP, we always start with the front view. So, draw A prime, B prime. Why A prime and B prime? Remember, A prime, B prime represent the front view labeling. At an angle, whichever angle you want to give it, theta or alpha, whichever. This is entirely up to your discretion. Okay, later in our practical classes will just be having specifics. Okay, now or later at the end of this lesson, I may be able to maybe solve one or two examples for you. Now, this is the true length, and the true length. Oh, and the true inclination with the HP. Okay. Step 3. You project it downward. Now from A prime and B prime, project lines downwards to HP. The fourth step is just to observe and visualize. The top view is shorter than the front view. Why? Because the line is inclined to HP. So that's why we see the top view is apparent length, not true length. Why is the top view shorter? It's very critical for us to understand this. Because when a line is inclined to the plane, that plane does not see its full length. It only sees the projection of the line, which is shorter. Now, let's come to the third image on the right. From the given data, the true length is 40 units, the inclination is 35 degrees. Okay? The heights are given relative to the HP and VP. Now observe the following. The front view shows the full 40 units, the true length. The top view is shorter than 40 units because it's inclined. So let me summarize. And this gives me the ability just to reinforce the rule that when a line is part of the VP, the front view will always give us the true length. But when it's inclined to the HP, the top view will give us the apparent length. Always I want to pay attention to common mistakes in such an orientation, the fourth orientation. Students often make this mistake. They draw the top view equal to the front view, and that is always incorrect. Please pay attention to that. Okay? Once the line is inclined to the plane, the view will never show the true length. Okay? Let me ask you. If you tilt your pen upward and look at it from above, your pencil, the HP that you're using or whichever to sketch, will it appear longer or shorter? Again, you want to give me the answer? Yes. Work with me. Then draw a slanted line, the front view. Shorter projection below. Say this is exactly the projection. Say this is exactly what the projection does. We've summarized. We've completed the 4 cases, the 4th orientation. So, what's the comparison between the 4 cases? The first orientation, second, and third. As usual, the first one, the first orientation, we saw that it was where we only get to see the front view, which gives us the true length. The second one, The top view gives us the true length. The third one, which there was a previous one, was both views. When it's parallel to both HP and VP, we get both views giving us the true length and the current orientation. The fourth one we're summarizing is when the front view only gives us what we call the true, or shows us the true length. Now we are seeing distortion begins. I repeat again, distortion begins. What's your takeaway? 1. When a line is inclined to a plane, that plane does not show the true length. Now let us reserve this case. A line inclined to VP and part to the HP. And you will notice the behavior will flip again. So, a quick one. How do you get to solve for this? Just solve above. As usual, your XY line. Draw the front view at an angle, the true length. Note the true length inclined at an angle. Project that downwards, the true length inclined but projected downward. Draw a shot at top view. Label. The first label is the front view, A prime, B prime, and also A, B. What do I mean here? Inclined gives us apparent length. Parallel gives us the true length. Only the plane to which the line is parallel shows the true length. In other words, it shows the truth. It speaks truth. Actual length. Let's move to the second last orientation. A line inclined to the VP or parallel to the VP. A line parallel to the VP, inclined to the VP but parallel to the HP. Sorry. Well, the fifth orientation. We have cruised through the 4 orientations, and here we come to the next orientation, a line that is inclined to the vertical plane. Now, I want you to notice something immediately. The case is a reverse of the previous one, as was the second orientation, a reverse of the first orientation. Okay, what does this mean? Prior to the HP, the line lies on the horizontal plane. Inclined to the VP, the line is tilted with respect to the vertical plane. So imagine this, a rod lying on the ground. It's a rod, a pipe. You're a mechanical engineer, you can just visualize a workshop whereby you're having some pipes on the floor, but slanted relative to the wall. Okay? Hypothetically. Okay. Let me start with the picture representation that we have here. The left image on your screen. Here you can see the line AB lies on the HP. It's not lifted, it's flat. But it's inclined at an angle theta to the VP. Okay? So now the inclination is not with the HP, it's with the VP. The inclination is not with the HP but with the vertical plane. Let's apply the rule. Very important. Now let's apply this main rule from our previous collections of rules. Number 6. Line shows its true length in the view where it's parallel to the plane. Just that one rule. So parallel to the HP, that's where we get to see the top view. Oh, the true length of the true length of the top view. Inclined to the VP, the front view will not show the true length. Beautiful? Yes, it is indeed beautiful. Now, so the top view shows the true length plus the true angle of inclination. The true angle of inclination. I didn't give the angle here, but you got it, okay? Front view is shorter than the true length is the apparent length. In the middle of the orthographic projection, okay, what do we have here? Now let us construct this step by step for your understanding by sketching with me, okay? Now, I'm gonna guide you, you do the sketching. Because from the previous example, I did a demonstration on the previous example on how to draw an XY reference line. That's the first thing. Okay. The second one is to draw the top view. From here, you've got to draw a line that is parallel to the HP. Why? It shows us the true length. It speaks the truth. Remember the rule from the previous conclusion of the fourth orientation? We begin with the top view, PQ. This is the true length and shows the true angle of inclination theta with VP. Okay? Now the third rule, or the third step, sorry, is to project it upward. From P and Q, project it upward to VP. And at VP, the next step now, you observe carefully. The front view P prime, Q prime is shorter than the top view. I think you've noted that already, because the line is inclined to the VP. So it says, I am shorter, I am not true, I am the apparent length. Because the line is inclined to the VP, because of the inclination of the line to the VP, VP cannot see its full length. It only sees the projection of the line. We go to the right image on the screen. From what is given, the true length is 40 units. The inclination angle is theta is in this case 30 degrees. The position related to the HP and VP is given. Now observe the following. The top view shows the 40 units. Okay? The front view is shorter than 40 units. As you can see, even by viewing it. This confirms our rule. So let us summarize this. Parallel to HP, which is on the top view, it shows the true length. Inclined to VP is visible only in the front view and is the apparent length. It has to speak the truth. So don't make this mistake if you're a student. By drawing both views equal, because it's incorrect. Once a line is inclined to a plane, the plane will not show the true length. If a line is lying on the ground, or slanted out to the wall, which view will show its true length? You want to drop that on in the comment section? Again, if a line is lying on the ground, but slanted relative to a wall, which view will show its true length? The floor, HP, wall, VP. Do you have an answer? Is it the top view? The front view? Don't tell me you're confusing this. It's the top view. Now, so what do you do in this case? Let's go to what we call comparison of the 5 orientations. Now we don't want to go to the first 3 orientations because already we know very well what we're talking about. We finished when they were perpendicular and parallel. The first 2 and parallel to each other. The fourth one now is inclined, and the fifth one inclined to either VP or HP. Now let's compare the 2 orientation of the fourth and the fifth orientation. Now what we notice from the current view is that only the top view will show us the true what length. Definitely the previous orientation will be vice versa of this, whereby the front view shows the true length. They are exact opposites. Okay, what you take away today? When a line is inclined to a plane, that plane shows only the apparent length. Repeat again. Hear me this. When a line is inclined to a plane, the plane shows only the apparent length. Now let's move to the general and most important case. A line is inclined to both the VP and HP. And in this case, neither will show the true length directly. But in the example of parallel to both HP and VP, both were showing the true length. Why is this not showing? Oh, preempted. Okay, before we get to know how to draw the solution, official, draw XY line, draw the top view, which gives you now the true length, start from known to unknown, and but at an angle, okay? The angle in this case was theta 30 degrees. Project it upward. Draw a shorter front view. Label it B, PQ. And now PQ is what? In this case, it's not P prime, but I started with P and Q. I've left it for you to fill in the gap. It's also P prime, Q prime. You're through with it. Label perfectly. Now, one thing to take home with you. Parallel gives you true length. Inclined, apparent length. The truth is only seen by the plane to which the line is parallel. You got that? Beautiful. Now let's move to the last orientation when a line is inclined to both. When a line is inclined to both. Beautiful. Let me give you a few minutes, a break of 1 minute, so you can do the last orientation. And we do one example of a drawing of the same, or now we're supposed to approach such kind of calculations or just drawing if faced with an actual problem. Okay, in a moment. Okay, class. Now we come to the final orientation and the most important orientation, a line that is inclined to both the vertical plane and the horizontal plane. And this is the most generous case, I suppose the third generous case of a line being parallel to both the VP and HP. Because in road engineering, most lines are not perfectly horizontal or vertical. Okay? They're inclined in space. What does that mean? The line is not parallel to the VP. The line is not parallel to the HP. The line is tilted in both directions. So it's a fully inclined line in space. And we've talked about space and coordinates, so we may not go deep into that one. But let me go to the picture drawing on your left, on the left of your screen. Here you can see the line AB is tilted upward from HP, tilted upward from HP, and also tilted away from VP. Pay attention, please. So it makes an angle alpha with HP, and let me say, okay, alpha or and beta with the VP. Now let's apply our main rule. It's just one rule. A line shows its true length only if the view where it is in the view where it's parallel to the plane. Now ask yourself, is the line parallel to the VP? No. Is the line parallel to HP? No. So what does that mean? Neither the front view nor the top view shows the true length. So we're going to start, because we've always known we have to start from the where we are able to where the line speaks the true length. The front view gives us the apparent length. The top view gives us the apparent length. Wow. Am I stuck here? Are you stuck? Are we stuck? No. Let's move. Let's go to the orthographic view or patterns that we have in the middle image. Okay. Let us now observe this in projection. If we were to draw, how do you proceed? As usual, you were to draw the horizontal line, right? The second step, assume the initial position. To solve this, we usually begin by assuming the line is parallel to one plane. One plane. Okay? The next thing is to introduce the inclination step by step. What do I mean by this? We, here in this case, on the third step, we tilt the line to a one plane. Okay, tilt it. Okay? And then tilt it to the second plane. This is why you see multiple construction on the right side, multiple construction on the right side. Okay? Now observe carefully. Please pay attention to this. Both views are shorter than the true length. Both views are inclined. And very important, the angles you see here are not the true angles. Now, let's refer to the right image on your screen. I want just to use what we call. I want to use the locus method in order to explain this. Okay. This construction shows how we obtain the final projection using the locus method. We rotate the line step by step. We track the movement of the endpoints and finally obtain the correct projection. This is how we solve real example problems. Okay? It's unfortunate that we have not done a locus of point in our drawing, but I'll do an example of that one later. Or now we get to draw a locus of a point. But yes, I think in our last semester we also did a locus of a point when we were tracing. Yeah. So in the same manner, this is what we're gonna do. But on a later one, I'll just explain later. So students often make this mistake. They assume that the angle seen in the front view or the top view is the true angle. That's incorrect. When a line is equal to both planes, neither shows the true angle. So let me ask you, if a line is not parallel to any plane, can any view show the true length? Definitely no. So if you were to draw a one inclined line, show two shorter projections. What will you observe? What you observe is what projection does. Now let us summarize all the orientations. We've done the first, the second, the third. Okay? The first three orientations, we saw that only the true length is shown or projection on the front view, the top view, and both view. The first orientation, the front view, the second one, top view, the third one, both views, because they were inclined to parallel to both VP and HP. The fourth orientation, one inclined to either VP or HP. We realize that the front view in the fourth orientation shows the true length. The fifth view, the fifth orientation is where the top view gives the true length. And it's quite unfortunate that in this generous orientation of the sixth one, there's no true length in neither of the top view nor the front view. This is the complete story of the projectional lines. If a line is not parallel to any plane, no view will show the true length directly. So now we understand all the six orientations. The next step is to learn on how to construct them in exam problems, because understanding is one thing, but constructing is what Hans marks. I know you'd like that much. maybe you could just say straight away, give us an example of what will be coming in our exams. No, but I want you to retain what you call knowledge, and it's very important for you to have an understanding and a foundation, not to memorize, but always understand. Now, the last one, I want you to sketch the following before we just go to our worked example. One, our reference line XY. Draw the initial line. Third, draw or show two inclined views. Indicate both of them are sure and both are inclined. That's the concept of what we call line when inclined to both the HP and VP. So, what's the key concept in this discussion? Oh, no parallel, no true length. Both views are apparent. Okay, that's it. Basically, when a line is inclined to both planes, neither planes sees the truth completely. Interesting. Yes. Now allow us to move to our practical worked examples. Probably it will draw our minds. I'll just give one two worked examples. So I will just work with me and we'll just call it the end of our learning curve. Okay. Here, let me just go straight away to that one example and maybe I'll explain to us on how we are supposed to solve it. Okay. So what do we have? What do we have in our worked example here? The question is very clear. It's a line that is parallel to both the VP and HP. Okay, and the question say, says or reads as following: a line CD 50 millimeters long as its end, C 50 millimeters above the HP, and 25 millimeters in front of the VP. The line is kept parallel to both HP and VP. You are to draw its projections. So how do we go about it? Now, class, before I start, let us first interpret the data directly and carefully. We are told one, the line is 50 meters long. Okay? One end, point C, is 15 meters above HP. The other end, the same point C is 25 millimeters in front of the VP. In front of the VP. Pay attention. Facts. And the line is parallel to both HP and VP. When you approach such an equation, say in this case, lay down a strategy of what is given to you and what is known. And these are the facts that we know about this entire question. So we are solving for the projection that we don't know yet how they're going to be visible. But we know factually about the line where it's lying. So immediately, from our theory, if a line is parallel to both HP and VP, what did we learn? The front view shows true length. The top view also shows the true length. I use a generous method as the first example. So both views will be parallel to the XY line. And there will be no traces. Hallelujah. So what am I saying? This is one of these construction cases because there is no inclination and no shortening, no apparent length. So both projections will have the same length as the actual length, which is 50 millimeters. So if you were to draw, or you were to draw now, because you now got to work with me, because this is I want to work with this example together. Follow the following procedure. First, draw a line XY reference line. The line represents the intersection of the vertical plane and the horizontal plane HP. The second step, locate point C in the front view. Now, you begin with the given position of point C. Since the point C is above 15 millimeters of the HP, in the front view, in this case, now C prime must be placed 15 millimeters above the XY lane. So, how do you go about it? Mark C prime above XY. Its dimension is 15 millimeters. Okay? See, this is because the distance above HP is always shown in the front view. I repeat again. It's simply because the distance of the distance above the HP is always shown in the front view. Remember the rule that we applied, or the general rule that we are using. Now the next step is very basic. Just locate the point C in the top view. Okay, how do you do that? You are told that it's 25 millimeters in front of the VP. So from the image you can see that its top view point C, I didn't see prime or double prime. C must be placed 25 millimeters the XY below the XY line. So what do? You draw projector down from C prime. Okay, mark point C below XY, whose length is 25 millimeters. This is because the distance in front of the VP is always shown in the top view. The next step, how do you solve this? Now, since the line is parallel to both the HP and VP, so the front view will show the true length structure, which is 50 millimeters. Although since the line is parallel to both planes, the front view will be parallel to the XY as well. We learned that orientation, which was the third orientation. Now, what do you do in this case? This is the fourth step. You draw from C prime, draw an horizontal line to the right. Okay? Whose length is 50 millimeters. Mark the endpoint, which is 50. Endpoint, which is D prime. C prime from point C prime, draw an horizontal line to the right. 1. Measure its length, which is 50 millimeters. 2. Mark the endpoint D, because we say a line has 2 points, the starting point and the endpoint. Now this becomes C prime, D prime. So make sure that it's 50 millimeters and accurate horizontally from C to get C prime to get D prime. The next step, the fifth step. What do we know? From point D prime, drop a projector downwards. Okay? Vertical projector down from D prime. You've done it. Now the last step we know very well. Since the line is also parallel to the HP, the top view will also show the true length. Again 50 millimeters, and it will also be parallel to the XY. So the next step, the sixth step is from point C, draw an horizontal line to meet the projection from D prime and mark the endpoint. I repeat again, draw an horizontal line to meet the projector from D prime and mark the end point. From point C, draw an horizontal line equal to 50 millimeters until it meets the projector from D prime. That gives you point D. So let me explain this of what we obtained through these processes or these steps, because we have completed both projections. C prime, D prime is the front view. C and D is the top view, and both are 50 millimeters long. In this factor, they are parallel to XY. That is exactly what we expect for a line parallel to the VP and HP. There's no vertical trace. There's no horizontal trace. This is correct. Why? Because the line is parallel to both planes. Also note that it does not meet at endpoint the VP, nor does it meet with the HP. So there's no vertical trace and no horizontal trace. So let us summarize this example clearly. What are you given? Always know this. No, I do not require you to be writing for me in just an engineering drawing class, but you should be able to dimension. But these are factual things that will help you to solve for this. Okay, CD is 50 millimeters. C is 50 millimeters above HP. If I were to mark, I will consider that. C is 25 millimeters in front of the VP, and the line that we are drawing is parallel to both HP and VP. Therefore, the front view will give us the true length, which is 50 millimeters, as well as the top view will give us the true length, which is equivalent to also the same length as 50 millimeters. Both views are parallel to XY, and finally, they have no traces. So, I have finished for this example. If you have any question, please drop in the comment section. I'll check it out towards the end of this lesson, and I'll just be able to respond effectively. Okay. Do we have another example that we want to learn? Maybe just to give you a little bit of another example before we complete our lesson. I said 2 examples are just enough for us today. Now, okay, what example would that work for us? Let me, don't know. Okay, let's use it. The second example, a line that is perpendicular to one plane and parallel to another plane. Now, what do we have in our example here? This, okay? Let's solve it, right? Okay, there we go. It says that a line 55 millimeters long as its end E, 50 millimeters above the HP and 25 millimeters in front of the VP. The line is kept perpendicular to the HP and parallel to the VP. Draw its projection. The first question I want to ask you, based on our orientations, where does it fall? The first or the second orientation? Or third orientation? Very important. Okay? If you have that understanding, you always get to know how to go about it. And given from the previous example and how we solved it, I'll just guide you through. But it's already solved there. But I want to guide you on how to draw it, and you're going to sketch it with me. Now, before drawing, let us interpret the question carefully. What do we know? What are we given? The line is EF, which is 55 millimeters long, and E is what? Is 15 millimeters above HP, and it's also 25 millimeters in front of the VP. The line is perpendicular to both the HP and parallel to, it's perpendicular to HP and parallel to the VP. Now, from our theory, this immediately tells us something very important. One, if a line is parallel to the VP, its front view shows the true length. That's what we learned, right? If a line is perpendicular to the HP, its top view becomes a point. Yes, those are the things that we learned. Now, what does this mean before drawing? So in this problem, the front view will be the vertical line of 55 millimeters. The top view will collapse into a single point. What do we just learned? And since the line is parallel to the VP, there will be no vertical trace. But since it is perpendicular to HP, it will have an horizontal trace. Well, beautiful. Now, solve with me. I'll walk you through. And by doing this, you'll have to sketch so you can move faster. The first step is where you want to draw the reference line, XY, which represents the intersection of VP and VP. So you've got to have a vertical line as well. Now, the second step, we are told that point E is 15 millimeters above HP, right? Now, this distance above HP it's always shown in the front view. So mark point E prime. Why E prime? Because it's we're talking about the front view, and the prime represent the front view. We did about the orientation of notations. Okay, 15 millimeters above the XY. The next step is to now solve for it. So what do? Draw point E prime above XY, label it 15 millimeters. Okay, the distance between. Okay, this is the front view of point E. The next step, the third step, what do we know before we draw? We also told that the point E is 25 millimeters in front of the VP. One, and that the distance in front of the VP is always shown in the top view one of the rules, okay? So from point E prime, drop a projector downward and mark point what? E at 25 millimeters below XY reference plane. So how do you go about that? The first, project the downward, project down from point E prime, point E below XY, label the 25 millimeters, the distance at which point E is lying from XY. The next step is just to draw the front view of the line. Before you draw it, what is known to us? Please pay attention. One, the line is parallel to the VP and perpendicular to HP. Since it's parallel to the HP, to VP, sorry, the front view shows the true length. Pay attention to the figure, which is 55 millimeters. And because the line is perpendicular to HP, it stands vertically. So from E prime, draw a vertical line 55 millimeters long upward and mark the upper end at F prime. So in a nutshell, three very basic steps: vertical line from E upward. Second, make the length which is 55 millimeters, that upward line, and label the upper point, the last point, by closing it with F as F prime. F prime. So E prime F prime is the front view, and it is the true length. Beautiful. Now the last step is to draw the top view. Here is just to observe carefully. Since the line is perpendicular to HP, when viewed from above, it collapses into a point. Remember, we talked about that. So the top view of E and F coincide with one as same points, EF. That means point F falls exactly on E. They coincide. So we write it as F in brackets E. So what are you supposed to do? In a nutshell, very simple. One, no extra line below. Just label the point, the same point as FE. So the top view is just a single point labeled as FE, comma E. Okay. Now let me explain about the traces. Let us interpret the traces shown in this solution. Do we have them? Yes, we have. Which one? Is it the HP or HT or VT? No, the VT. We don't have the vertical trace because the line is parallel to the VP. Therefore, it never meets VP. It won't have a vertical trace. So we have only the HT because the line is also is an horizontal line, an horizontal trace because its line is extended or considered with the respect to HP. It means HP at the vertical alignment below the XY reference line. Simple period. So what do we have here finally? Now the projection are complete. We have obtained E prime F prime is the front view. It shows the true length, which is 55 millimeters. F comma E is the top view, and the top view is just a point. So this is exactly what we expect for a line perpendicular to HP in parallel to the VP. Let us summarize this example clearly. What is given to us? F 55 millimeters. E is 15 millimeters above HP. E is 25 millimeters in front of the VP. The line is perpendicular to the HP. The line is parallel to the VP. Therefore, the front view shows that the true length, which is 55 millimeters. The top view is just equal to just a point. There's no vertical trace. The horizontal trace exists or is available. And that marks us to an end of our solving of the second example. Now, I want to emphasize this. When a line is perpendicular to a plane, its projection on that plane becomes a point. When a line is parallel to a plane, the view shows the true length. Why is the top view not drawn as a line here? The answer is very simple. Because the line is perpendicular to HP, and therefore its projection on the HP collapses into just a point, a dot. So this example confirms that what we study in the first orientation, now we can move to the next practical case and continue applying the same logic here and there on examples related to this. In our later lectures, we'll just go to other examples, and we'll go deeper into the other orientation that we haven't handled here, like the second, the fifth, and the sixth, and as well as the fourth orientation examples, which will give you just an holistic understanding, or will lay a good foundation for your understanding on how to tackle problems in regards to projection of lines. And before we finish, I would like to request you to take some time and respond to a number of your queries that you may have. Raise them in the chat section, and I'm here to address them. Okay. All right. That brings us to the end of today's session. Now take a moment and reflect. We've moved from understanding points to building lines, to exploring all the fixed orientation of lines, and even solving practical problems step by step. And if you followed carefully, projection of lines should no longer feel complicated. It should now feel logical. But here is the exciting part. In our next lesson, we are stepping into something bigger. We are moving into projection of solids. And this is where everything you've learned today becomes extremely important. Because solids are made of edges, edges are lines, and now you understand the lines. Okay? Now, before you leave, don't leave with confusion. If there's anything that is not clear, please drop your question in the comment section right now. Even a simple question is welcome. You don't have to exactly specify your name or anything. Just drop a comment and I'll just respond it either in the group section or just later. I can just do a video to address that. And for those watching who are not my direct students, you are most welcome here at this lesson. If this lesson has helped you, hit the subscription button, like the video, and share it with someone learning engineering drawing, because we are building a space where engineering becomes simple and understandable. All right, I'll see you in the next class. Projection of solid. Let's keep building beautiful. Thank you. Thank you.